All right, let's take a look at vector math. In the last video, I introduced the ideas of vectors and a couple things when you're adding and subtracting vectors before we get started. The main rule of adding vectors and subtracting vectors is that when you add vectors, subtract vectors, they need to have the same units. This is probably common sense and something you know from math class, but just keep that in mind as we do our vector math. So let's say we have this situation here where you have the person living in the teal house, and they're going to walk to their friend's yellow house before they walk to school. So they take path A. Okay, so we have a displacement vector, describes the magnitude, how many meters they walked in the direction. And then we could also have a vector B describing their path from the friend's house to the school with magnitude and direction. So this friend's path could be described simply as this vector C. So the way we would add vector A to vector B is very simple. And this is similarly how you add vectors. We can draw vector A out. So let's say this is vector A. Here's vector A. And we have vector B here. And the way we add vectors is always the tip of one vector, this is the tip of this vector, to the tail of the other vector. So I'm going to draw the tail to the tip of that vector. So there's vector B, right? So we've got the tip to tail. And then from the tail of vector A to the tip of vector B, we draw what's known, do a little dash line, as a new vector, and this vector is known as the resultant vector. So the resultant vector is the vector that you get when you add A to B. So when you add two vectors, you go tip to tail. In this situation, if this is the resultant, these are known as the component vectors. They make up the resultant. So instead of your friend going boom to boom, your friend could have just gone boom. Okay, but they didn't. So the resultant vector did not actually happen, but it could have, and it would have given the same end result. So let's take a look at two people involved in a marathon that take two different paths but reach the same point. They start at the same point and they end at the same point, but you can see the order at which they did their running was different. And it leads to three rules of vectors. So here are the three rules of vector math. Okay, the first rule of vector math. So let's say your friend walks 5 meters in this direction and 10 meters south. We have these two vectors and we want to add them. So rule number one says they can be moved parallel to themselves in a diagram. And we often do that to make sure that if we're adding them, A plus B, that they are lined up tip to tail. So I can move B like this. So I can move B parallel to itself as long as it's staying in the same direction, and I can move it so that it is tip to tail with vector A. See, it normally started this way, but 10 meters south is the same there as it is there. And now they're tip to tail, so now I can draw my resultant vector. Okay, so first rule, vectors can be moved parallel to themselves in a diagram. Okay, the second rule of vector math is that vectors can be added to each other in any order. Okay, let's think about this situation. Let's say that somebody walks 5 meters east. Whoop, I forgot my unit. So 5 meters, 10 meters. So let's say they walk 5 meters east, then they walk 10 meters south, and then they walk 5 meters west. So to get the result, in the order these vectors are added does not matter. So let's take a look at a couple of different paths they could take. Let's say they walked 5 meters east, then 10 meters south, and then 5 meters west. They would have ended up there. Now let's say they start and they go 5 meters east, but then instead of doing 10 meters south first, we'll do 5 meters east again. So they're here, and then they walk 10 meters south, they still end up at the same point, right? They would have no matter which order these vectors are added. So vectors can be added in any order. And the last rule is to subtract a vector, add its opposite. Let's say we had two vectors. We had vector A, which was 5 meters, and vector B, which was 5 meters. And I said, what is A minus B? What does that equal? So what we would do is we would draw out vector A. So there's vector A. And we're going to add it to the opposite of B. Well, B is also positive 5 meters. So B looks like this. B looks just like A. It's 5 meters. But since we're subtracting them, right, here's vector B, here's vector A. Since we're subtracting them, what I'm going to do is I'm going to flip this vector B 180 degrees. So it's this. So it's 5 meters this way. So here we have the two 5-meter vectors. One is east, one is west, or one is to the right, one is to the left. They're both 5 meters. So the end result is 0 in that case. Okay, so all we did to subtract is we added the opposite. And to make a vector an opposite, you turn it 180 degrees. And I'm going to add rule I'm going to add rule 3A here. And that is this. That is this. If you multiply or divide a vector by a scalar, it still is a vector. For example, if a cabbie is driving with a certain velocity vector v, and we want him to go twice as fast, we could say we want 2v, and all that would be an arrow twice as long as our original vector, right? So 2v would look like this, but we still have a scalar. We still have a vector. So does this vector math actually work in real life? In other words, let's imagine we had a gun that could shoot a ball at 100 miles per hour. Let's say 100 meters per second. Okay, so here's this gun that shoots a ball 100 meters per second. It shoots it to the right. What if we put it in a truck that was moving this direction? Whoops, excuse me. That was moving the exact opposite direction at exactly the same speed. Well, if we think about what we know about vector math to this point, if I were to add those two vectors together, they would result in a velocity of 0 meters per second. So what if we took a gun that shot about 100 meters per second, put it in a truck going this way at 100 meters per second, and shot the gun? We should see a velocity of 0 meters per second. And that's exactly what the Mythbusters did. So let's watch.
Can an object shot backwards while traveling forwards ever drop straight to the ground? It's a fascinating thought, but trying to prove it is bringing our physics team unraveled. Tori, Carrie, and Grant are struggling to prove the supposedly common sense myth that an object drops straight to the ground when its forward and backward momentum are exactly the same. With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that. Fantastic. I mean, look, it doesn't move at all. It's going straight down. Dude.
Woo! We did it! We did it! Yeah! Vector addition! Woo! We canceled that velocity.
So what you see, she just said vector addition. She's talking about what we're studying, but the ball was fired in this direction. No, it's hard to see. And the truck was moving in this direction, and they had the exact same magnitude, but exact opposite directions. The vectors added up to 0, so the ball just fell straight to the ground, which is pretty darn cool.
We did it! We did it! Yeah! Vector addition! It cancels out velocity.
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.